completely aluminium. Okay, I've just updated the schedule that I had put on Conto. The earlier version was just this part, but I've also added the groups, Group A and Group B, because as you can see, this week we are doing both A and B together. So we'll have 4 hours today and 4 hours tomorrow lecture, everyone together. But from next week on, Group A will have Thursdays and Group B will have Fridays. So you'll have 4 hours each every week. So that will be divided. And the groups have basically been set alphabetically. I've just divided you into two. The reason I've done it is just to make it more quickly. So I've divided it into two that way. As you can see, I've made comments here. I have a 4-hour lecture there, and I have no lecture next week. That's because next week I'm up at Stord for my own studies. Which was a real bummer that they couldn't move me, because they have two groups on that study. They have two groups. One group that has to do Thursdays and Fridays, and one group that has to do Mondays and Tuesdays. And if I had Mondays and Tuesdays, I would only have to move one lecture, but now I have to move my entire Fridays and Thursdays instead, because they had so many students that they couldn't start. If they moved one student, then they had to suddenly move everyone who needed to be moved. So that would have been a huge job for them. So I sort of understand it, but it was really, if I had known that they were going to divide it like that, I would have been on them before they set the class lists. Check your hands. Yeah, 4-hour lectures this week, 4-hour lectures in week 41 and week 44 also. So week 42 I'm at Stord, and week 45 I'm at Stord, and week 46 then we're past the entire curriculum for this. We've done everything, so that week is open for you to just use the room for your projects and your submissions and stuff. So as you can see, we have 3 submissions. Submission 1 will be released, and you'll have about 2 weeks, a little over 2 weeks to get it. Same with submission 2, a little over 2 weeks. You'll get a week off between 1 and 2, but between 2 and 3 you won't really get a week off, because it has to be done by here, I think, because those 3 submissions plus the project that you're going to do together, they are 40% of your grade in this course. So the submissions, they will be purely inventor submissions. You will do them individually. So you will get an assignment. You will get a part that you are going to model, create a 3D model of, and then you are going to make a 2-dimensional drawing of it, and that's what you're going to submit for it. And the whole point is that if you do a lot of mistakes in the first one, that's not a big problem. It's not going to pull your grade straight down. But what's going to pull your grade down is if you make the same mistakes in the second one and the same mistakes in the third one. So if you keep making the same mistakes, because between these I am going to comment them, so that you will get comments on what mistakes have you made on this one. So if you don't check your comments and avoid making the same mistakes, that's going to have a negative impact on your grade. But as long as I can see that you have progressed, you've learned a lot of stuff, you've made some new mistakes later on, but that's not a problem. Everyone makes mistakes, especially in something like this where we have such a little time to learn it. Professional CAD drawers, they go to school for 2 years, and then they have 2 years as an apprentice, if you're going to have that as a vocation. While we engineers were supposed to learn it in a couple of weeks during fall. So it's quite a difference. So no one is expecting you to create perfect drawings. If you manage to create perfect drawings, hey, that's perfect. Nothing better. But there will be mistakes, and that's not a problem. So you shouldn't be, if there is a lot of comments on your first submission, don't be afraid. It's not going to be a huge problem. Just learn from them and correct them for the next submissions. So those three are individuals. So that you do them one by one. In the project, you will be divided into groups of 3 or 4, but I'm going to talk more about the project afterwards. So I'll do that then. So already next week, you have just study time, and that will be in room 1093 down in the first floor, because 2084, which is normally used, it's just jam-packed when it's fall semester. So what we decided to do was put you down there, and we divided you into 2 anyway. We were going to divide you into 2 anyway, and then it's not a problem to be there because there's plenty of room for 20 in the room downstairs. We have room for 40 in the one up here, so it's sort of silly to be 16, 17 students in there, and making sure that no one else can use the room for 4 hours or 16 hours, 8 hours every week. So since we had the other room available, we used that one. Yeah, but since you already have CAD study next week, I can start lecturing you on practice task 1 and 2 until 2 weeks. But you are very welcome to start already. As you will see as we progress along the compendium today and tomorrow, you will see that I've made a fairly step-by-step guide on all of the practice tasks, so that it should be plenty possible for you to start work on your own for it. And also you will have, you're supposed to have 4 student assistants, but I think that Gabriella is going away for a week or 2. Now I'm not sure if, I think it's next Wednesday she's going away, so you will only have 3 student assistants, but still you'll have 3 student assistants available to help you if you're completely stuck on something. Yeah. As I said, this one is up on Fonto. So it's here in the, you go to the CAD folder, you have the CAD schedule. I think Einald has put in a scheduler. I think he has CAD stuff in that one too, but just disregard it. Yeah, he basically just have the times put in for CAD when we start. So just follow the CAD schedule in the CAD folder instead for the CAD stuff, because that's telling you what you're going to do, what we are going to work on and everything. We also have the compendium, so this one, which we're going to deliver out now, is also in a PDF here. And that is a little bit because of there's a lot of links inside it to YouTube videos. So that's, you can either just search for the name of the YouTube video, or you can open the PDF and just click. All of the YouTube videos are on my own personal channel, so that's easy to find anyway. Don't be all that worried about the thickness of it. There's a lot of screenshots in there, so they take a lot of room. So there's not that much text in it. So have everyone gotten a copy? Perfect. Just keep this up. The students' assistants are supposed to have copies too. There's supposed to be too many. Right, so we've got the compendium there, which you can use as a PDF for links and stuff. You also have what I put in there, which is a drawing checklist. We'll get to that when we are going through the curriculum. But that's basically just to help you. It's something that you can, whether you want to print it or if you want to just keep it up on your screen while you're going through it. That's up to you. But it's basically a list which tells you if you have checked everything in your drawing. So have you checked that the part is shown in its operating position, are all necessary views and sections in place, stuff like that. So it just make you think about your drawing before you submit it. So it's intended for use with the submissions. But basically, if you're working for a company that does mechanical design, they usually have their own versions of these lists. So that you have to, and often they have a system where you actually, either electronically or manually, you have to fill them out. So you actually have to tick the boxes that you've done this, and then you have to sign it, and then this is archived along with the drawing. Which means that if they later on discover that, well, not all of the dimensions necessary to produce the part is there in the drawing. They're just missing a lot of dimensions, and you've actually ticked that box and signed the sheet. Then you're sort of, whoops, I've not done my job properly. So it's sort of a quality system check. And that's smart for you to use also for these submissions, because you can get a lot of information that you just by reading through these, you'll get a lot of reminders to, well, have I remembered putting on these dimensions now and everything. So it's a nice tool to use. Yeah. Then we'll start with the project. I'll just go through that one. So it's a group project or a team project or whatever you want to call it. You're going to design a lifting equipment, which is to be used with a girder crane. So this is an illustration of a girder crane. It has a trolley up here, which can move this way, and it also can move this entire girder, can be moved that way. So it has X and Y coordinates, so it can move in two directions. It has a hook at the tip, and you can lower the wire down, and then you can lift stuff with it. So if you ever been inside industrial warehouses and stuff, they use this all the time. So the project description, we have a customer which is in need of bespoke lifting equipment. Bespoke means that it's custom made for their need. So it's, I think bespoke is a synonym is tailor-made for it. So it's something that you are designing for the customer for their exact purpose. And they are going to use it with their girder crane. They are going to attach the lifting equipment to the girder crane hook by using a green pin standard shackle. So you can see there's a link there, which puts you into a PDF document. And this is the kind of shackle that's going to be used. So basically the hook is going to hook into the top part of the shackle, while this green pin is going to go into your lifting equipment. So you have to have some interface in your lifting equipment that allows for you to fasten this shackle onto it. And let's see.
It isn't aluminium. I should have noticed because aluminium has a different potential. It has
and the shackle is to have a working load limit, a VLL, of 1 metric ton. So then you have to just go into the tables in that PDF for the green pin shackles, and you will find workload limit 1 ton, and there you will have all of the dimensions given, so that you will know how your design has to look with regards to the shackle. This means that the lifting equipment will also have a workload limit of 1 metric ton. We could have told it, we could have put it to something more. Then we would have made the shackle as the weak point in the system. So you would still only be allowed to lift 1 ton with the shackle in place there. But usually you always try, when you're designing stuff that's going to use shackles, you always try to design it to the specific shackle. So that if the shackle has a workload limit of 1 ton, as in here, you will also design for a workload limit of 1 ton in your design. And it is to be in accordance with a European Commission directive. It is the machine directive, it's actually called. And it's classified as lifting accessory. So what I would recommend for you then is you click link, you get the PDF up, and this is how many standards look like. It's a shitload of text, basically, and it can be really difficult to find what you're looking for here. But I've given you a little hint by telling you that it's a lifting accessory. So what you can do is you use Control F so that you get the search bar up there, and you put in, just as you see it here, lifting accessory, and then it will show you all of the places in the text where it says lifting accessory. That's a very nice way of skimming through a huge standard. Some of the standards, they can be 500, 600, 700 pages. And maybe all the stuff that you need is maximum 1 page combined. Then it's really nice to have them electronic and be able to search through them. So it's a nice tool to use. Which means that inside here you will find your safety factors that you need to use when you're designing. When you're doing your calculations for your design, you will find the safety factors inside the machine directive. So, the lifting equipment shall make use of the lifting motion itself, so the force of gravity, or other means, a pressurized air, pneumatic, or hydraulic, or electric, etc., to grip the object that is to be lifted. Because you're going to lift something, each team will have a separate object that they are going to lift, so they will have to do the entire design from the shackle and down to lifting the object. If you are using other means, pneumatic, hydraulic, electric, whatever, maybe you're using suction cups or something, then it is enough that you go to Google, you find some company that delivers this kind of gear. Then you find their data sheets, maybe some drawings and stuff of what you need to use. And then you just appendix this into your report. And then you create your lifting equipment around this other manufacturer's equipment. That's a very common way to do it. So if you, let us say you're lifting a box and you intend to use a suction cup up top, and then you have some contraption that you design here, and then you have the shackle up there. So this part here will be from another manufacturer. That's not a part of your design directly. Your design is this part in the middle, and the fact that you can put a shackle on it, and that this one is connected to it. So that's your part of the design. You just have to show me what other stuff you intend to use in your design. But if you can, I would advise you to try to challenge yourself to find ways of using gravity to do this. So that if there is some way that you can make the make the mechanism. If we have this one again, if there is some way you can have some claws or something that will grip it on both sides, and then through some mechanism in here, it will be as soon as you start lifting it, these claws will press in and hold it tight. So that's other ways of doing it. So those can be quite fun to look at, because you get to look at levers and everything and how you're going to design it. So it can be it's a bit more. It can be a bit more challenging using the force of gravity, but it is also more satisfying when you see how you can do it. So we have several teams, and each team will be assigned a different object, as I said. And this also means that each team has to find their own solution, because none of the objects are alike, so that you won't have to. It won't be possible to sort of borrow ideas from. Well, maybe you can borrow and adapt ideas from other teams, but you can't borrow them directly. That's pretty impossible. And I've already assigned the teams, 3 or 4 members for each team. The reason that I've already assigned them is that it's to simulate a work situation, because unless you have quite a lot of experience and are in a position where you are a project leader, you are not able to choose. Unless you are a project leader, you're not able to choose who your team members are. If you're a project leader, you can usually say, well, I need that guy, and him to put them on my team. Then we can do this job. But usually, as a freshly educated engineer, you are the lowest ranking member of the team. So then you can't get to choose anything. So that's why I've just put everyone into groups, so that we have you sort of just have to find a way of working together if you're not used to working together. So team 1, going to lift a sphere. I'm actually going to find it here. So team 1 is going to lift a sphere, a ball. It has a diameter of 1 meter and it weighs 1 ton. So it's going to use the entire workload limits of the equipment. So I put this one up here. The team 1 can, in the break, you can come and pick up this one. So I have one for each team. And the team members, you get them here. As I said before, I'm not going to try to pronounce much here. You have team 2 are going to do a vertical cylinder. Which means that the cylinder is going to be placed vertically on the ground, so you're going to have to be able to lift this in some way or other. Let's see here, team 2. And here we have the team members of team 2. Team 3 will have also a cylinder, but now it will be horizontal instead. So that's a different way of lifting it. This one. And this is team 3. Team 4 will have a triangular pyramid. So it's not a Egyptian pyramid, because an Egyptian pyramid has a quadratic base, but this one has a triangular base. So it's like this instead. So it only has 3 sides. So we have this one.
We've already looked at it a bit with the motion and the galvanic in there. The electrode
And the team members are up here.
we looked at there was we looked at
As you can see, most of them have some variation of 1 meter and 1 ton. So it's a diameter of 1 meter, side length of 1 meter. The ones that are cylinders, they have a length of 2 meters instead, just to get them a bit longer than the diameter. Team 5 will have a triangular rod. So it has 3 sides, but it's going to be vertical instead. The team members. We have a horizontal triangular rod for Team 6, so it's basically the same as Team 5 on the horizontal instead of vertical. And the team members are here. Team 7, they have a cube. So a cube will be fairly similar to what I drew on the whiteboard. And the team members. Team 8 will have a vertical quadratic rod. So it's this one, vertical. And the team members are Team 9 will have a horizontal quadratic rod. And the team members are and Team 10 will have a flat plate. So we'll be lying horizontally, the entire plate. The problem there will basically be to get a grip on the sides or something if you're going to try to lift it somehow. And the team members. Mostly this has been done through alphabetically. I've just picked people into teams, so there is not much forethought that I put into who I've put into which team. It's basically done from the attendance list for Group A and Group B, and I just pick people. So it's fairly random, everything. During the semester, we will have some progress status meetings. And those status meetings will be done with the team representatives, so all of the team members, and representatives of the customers, which will be either me or Torbjörn. So for the first, I think I'll get that later on. So we have two mandatory meetings, so there are 2 meetings which you have to have with us. And then we can schedule extra emergency meetings if needed, so that if you end up with, if you've had the 2 meetings, you've ended up with a design that you're going to continue going with, you've chosen your solution, and then you suddenly figure out that, whoa, this isn't going to work at all. We need to do something completely different instead. Then you are allowed to schedule emergency meeting with one of us, so that you can sort of get a little bit of feedback on what other solution you should choose. But Me and Torbjørn, we have some experience in this, so we should be able to sort of direct you into a workable solution first off. So I think it will be enough with the two meetings to get you into the correct solution, but as I said, emergency meetings can be done. For the first meeting you will have, the team will have, both me and Torbjørn will be there. That is just to introduce Torbjørn a bit to what we're doing in the project, because I have the main responsibility for the project. So Torbjørn is going to be with me for the first meeting, and then afterwards I will do all the meetings for team 1 to 5, and Torbjørn will do team 6 to 10. And if Torbjørn is a bit unsure on something, I have the final say, so that if there is some sort of confusion in one of the teams as to what they're going to do and stuff, Torbjørn will consult me, and then we'll figure out something to do. So each team is responsible for scheduling and creating the agenda for their own meetings. This is also to simulate the work life, because most people, or at least most engineers, hate meetings. So if you need a meeting, you usually have to handle it yourself. You have to send out invitations and make sure that everyone can fit it into the schedule and stuff like that. So, and also creating the agenda, which is sort of just a bullet point list of what are we going to do during this meeting, which is nice to have beforehand, because then everyone who's showing up to the meeting knows sort of what we are going to talk about. We are going to try to keep the minute length to only 50 minutes. This is also something that comes from a workplace. Because, as we all know, time is money. So in a workplace, if you have unnecessary long meetings, if you have scheduled a 2-hour meeting and after 1 hour you are basically done with everything you needed to do, but everyone is just sitting around because, well, we're supposed to have this meeting, then it's money down the drain basically, because no one is doing anything productive. So 50 minutes is really short. Usually companies have a policy of like half hour or something, 30 minutes for meetings. But 50 minutes is just so that we will feel that time pressure when we are doing the meetings. So it's important that you stay on point and that you ask concise questions, and that it is also important for me and Torbjørn that we try to avoid digressions, that we start telling you about other stuff that we've done, or we telling stories and everything like that. That's for our breaks. That's not for our meetings. Yeah, and the meetings will also be a part of the assessment process for the project. So the team has to make a report, or not a report, but a summary of each meeting, which is supposed to be appendix to the report at the end of the semester. So the first mandatory meeting shall be held before the 16th of September. So you've got less than a month for it. And you are to submit a single-page presentation beforehand. I will open up a folder on a submission folder on Fanto where you can put it up. Basically, that can be a hand-drawn page, which I've just scanned, and you submit the PDF. That's not a problem at all. Because what we are after in this one is that the team comes together and you brainstorm different ways. So how can we manage to lift this stuff? Well, we got something like this. We can use suction cups. Maybe we could have some sort of beam, some claws on the sides, and some hydraulics in here. So you can sort of just put down almost all of the ideas that you managed to come up with during your brainstorming session, even if they sound pretty wild. If they sound like, oh, this is going to be very expensive to do, just put them in there, because then you have them for the meeting, and then we can, when we have the meeting, we can just say that, well, this one is going to be expensive, we're not going to look more at this one. We're going to look at these, because these look like they can work. So that's the point with this first meeting, where you are just basically going to look at all different possibilities of your design. And we will discuss all of these possibilities during the meeting, and we will choose one specific a specific one of the designs that you are going to work on from that point on. Then we're going to have a second mandatory meeting. That's a month later, approximately 14th of October. And now you're going to submit a draft of your project report. And this means that you don't have to have done something on every single part of the report. If you haven't gotten to your calculations yet, you just make a heading, calculations, and you leave it open. You haven't done this part yet. This is just a draft, just to show how far you have gotten with the report. It will have its own submission folder on Fonto. And you can also see further down in these team project descriptions, you will see hints at how the report should look like. And during this second meeting, we will discuss what has been done so far. Have you done a lot? Have you done a little? So that you have to step up your work for the rest of the semester. And then we're going to make a plan for completing the project. So that we will maybe sit down and say, well, within the next 2 weeks you should have designed these parts, and within the following weeks you should have designed those parts, and stuff like that. We'll just make a very quick plan for you to try to follow in order to be done within the deadline. So the end product is also going to be submitted on Fonto in the submission folder, and you're going to create a zipped folder. Basically what you do is you put everything into one folder in Windows Explorer, then you right click that folder and you send to a zipped file. So you just zip the entire stuff and then you submit it. Because then everything will be inside there, both the project report and all of your 3D models and your 2D drawings, everything will be inside that folder, and then it's a lot easier for me to correct everything. So it's going to contain a project report, which will be in accordance with the form rules of a bachelor thesis. The form rules of a bachelor thesis, as far as I know, haven't been translated from Norwegian to English yet. So I've made a sort of summary with what I want at the end of this document, just so that you know a bit more. But I think Fredrik is on it to get someone to translate this stuff, because you don't really need it now, because I've already given you all the information you need to create a project later on in this document. But you're going to need it next fall semester when you're going to do your bachelor thesis. So it has to be translated sooner or later anyway. And in the project reports, you're going to put in your brainstorming phase. So just a little bit of text explaining the different designs that you had in your brainstorming phase. It doesn't have to be much, a couple of lines just describing your thoughts around that specific designs, and maybe a pro and a con for it. Does it look like it's going to be very successful, but it's going to be very expensive? So just a little bit of that. The planning and design phase, you have to put in there. So after the first meeting, when we have chosen a design, then all the work you do from there on, you should try to document it somehow. Whether just making a couple of paragraphs every now and then on what has been done. Your design calculations has to be a part of it. That's directly connected to Torbjørn's part of the lectures, where he does the calculation part of the lectures. So basically, you have to use what he teaches you, and you have to transfer it to your own design to see, well, exactly where do I have to do calculations and where can I sort of skip calculations.
Not a problem, especially for the hydraulics part.
You will also have a short cost analysis part. This is just to make it feel a bit more real when you're doing it. Of course, manufacturing costs, that will be pretty impossible to get an actual cost on. But it would be nice if you try to just wing it, so try to guess how much it would cost to manufacture it. So that if you know that you have a lot of welding, you know that, oh, it's going to be quite a lot of hours of welding, and you're not quite sure what an hour of welding costs, but you can just try to put in some figures and try to get something there. What you can do is material costs. That you can get from suppliers. You can just go to their web pages and see what kind of materials you need, and then you can get their cost from there. Often it will be cost per kilogram or cost per cubic meter or something like that. Or if there are pipes and stuff, then it's cost per meter length. So it's very easy to get the material costs right. But that's not something I'm going to sort of go in and check and see that, oh, you're completely missed out on that price there. That's not the main thing. The main thing here is to teach you that often engineers have to keep an eye on costs for materials. We often have to, if I'm thinking about using some material which could be a bit more expensive than what I normally use for parts of the design, then I might have to look into the suppliers. Well, what exactly does it cost? How much material will I have to use here? What's that going to cost? So then we get into a bit more of the actual work of an engineer when you're designing. You have to look at this stuff. Because if you just ignore prices of materials and costs and everything completely, and you just design the thing and you send it to the purchasers that are supposed to get all of these materials, and they are going to say, whoa, I'm not using all of that money. So then you have to go back to the drawing board and you have to start over again. So that's why it's more efficient to just keep an eye on it all the time. You're also going to have an appendix in the project reports. The appendix will contain the technical drawing package, so all of the 2D drawings that you will create for your parts, the manufacturing drawings, basically. It will also contain the data sheets or information on purchased parts. If you're going to use like a suction cup or a hydraulic cylinder or something like that, then you need to add that as an appendix, the information that you get from that supplier's webpage. It shouldn't be necessary to actually call suppliers and ask them questions and stuff. If you can't find it on their webpage, try a different supplier. Basically, it's the suppliers who haven't stepped up their game and gotten everything up on their web pages, they are losing out on a lot of customers. That's for sure. In addition, we're going to have a declaration of independent work. Yeah. Yeah. Well, just do this slide first. So we'll have a declaration of independent work, which is just all of the team members are signing that this is your independent work. It is something that we are required to add when we are grading a submission like this, because that is basically if it's found that you have directly copied someone else, that you violated the regulations of the school and stuff. You declare that you've done this yourself. So if we later on figure out that you've copied it directly from someone else, then the grade won't be valid anymore. It will also contain the 3D CAD models of everything for your design. and a 3D animation of each assembly. That's something that you're going to learn all the way at the end of the year. So that's something that you're going to use the last study, CAD study, on creating basically. In addition, everyone is to submit a one-page evaluation of the teamwork, and the evaluations will only be viewed by me and Torbjørn. They will be kept in a locked archive. Apart from that, which means that you are encouraged to speak your own mind about the teamwork. So that if you feel that you've been pulling most of the weight for the team and that the others haven't done their part properly, then you are allowed to write this in the one-page report. It is not because we are going to try to give poor grades to those who didn't pull their weight, but it is because we are going to try to evaluate how well you have functioned together as a team. Because it might actually be the guy that's pulling all the weights who's the problem, because he might not be telling the others to do stuff. Because if you're pulling all the weight in a team, what you actually should be doing is you should be telling your team members, well, wait, I can't do all of this on my own. I need some help from you. Can you do this and you do that? That's the best way of solving these problems. So it's just you're also free to be a bit self-critical if you feel that you did this, that you pulled a lot of stuff from the others and ended up being swamped with work yourself. And you're allowed to write this too. It won't be negative for your grade in any way. It's just a way for us to see that try to get a sort of view into how your every day of working with this team has been, because that's something we can't deduce that from a project reports and the rest that you have delivered. Yeah.
Do you want to criticize your team members, or can you still talk about them or something like that?
If you are proud of your team members, you have to put that in there. If you're proud of them too. So it's not just about criticizing or anything. If you feel that some of the team members have done very good work, put that in. It's just to sort of show us how we've been working. So it's not. It's a part of the. It's a part of the project in that manner, but it's not directly related to the grade. It's more like, did this actually work? So, yeah, then we do a break.
Very expensive.
Right. Then we'll move on to the compendium in computer-aided design, CAD as it's short. So you can see there's a pretty huge table of contents. That's because there's a lot of sub-chapters in this one, and each sub-chapter is like half a page mostly, and then there's most of that is a screenshot and stuff, so that it's the entire compendium seems a lot thicker than it actually is. There's not that much text in it compared to the thickness of the sheets of paper. So we are going to be using Inventor from Autodesk. You were briefly introduced to it in your first semester. Since then, we have gotten a new edition of the software. I was told when I started making this compendium at the beginning of the summer, right after the exam period, I was told that we were going to be using Inventor 2016. And I asked specifically because I was installing it on my computer in the office, because I saw that, well, there is a 2017 version out too. So wouldn't it be better to use the 2017? No, they were going to install 2016 in the computer labs. Well, what did they do now? A few weeks ago, they installed 2017. so I made this one from 2016, using Inventor 2016 on my office computer. But there's not a whole lot of difference between 2016 and 2017. So Usually the differences are when you get really deep into the complex functions, which we are not really going to touch on because that's too much to handle in a brief course like this. And that's where you actually start seeing differences in stuff. So when I attended school here, we had 2012, and when I started work at Imenco, we had 2014. And there was quite a lot of difference there because then they went from a fairly dark background to a more grayish stuff, and so the entire visual appearance was changed from 2012 to 2014. But still, the functions were the same. So long as you had learned how to use the software, then you knew where everything was. So there's not really much difference from 2016 to 2017 as far as I can see. So you'll just have to bear with me that it says 2016 everywhere in this one. So the literature is, of course, the compendium I've created. It's also the Fundamentals of Machine Elements, which is the book that Torbjørn will be lecturing from. And of course, it's not the entire book there. That's like 500-600 pages or something. I can't quite remember, but that's a very good book from what I have seen of it. It seems to be very, very thorough, and it does a lot of good explanations in it. We won't really be using that book in the CAD parts, but it is a part of the project, of course, because you have to do design calculations, and that's your textbook for design calculations. You also have the Mechanical and Metal Trades Handbook, which is the other smaller book that you have. It has several, I actually forgot to bring it today, but it has one section which is marked with, you will see that it has these cutouts for your thumbs to peruse it quickly. One of the cutouts is marked with TD. It's marked with TD, and in that cutout. And that's technical drawing. And that one is very good to use in this course. That's mainly what the compendium is using also. I'm using that part of that book. You will also have in the other parts of the book, in the other cutouts, you have design and you have calculations and stuff that you can look at there. So it's a really a good book to use. Now, I'm not quite sure what Torbjørn has decided to do there, but I know that there has been talk about letting you bring this book to the exam, but I'm not going to mix in that discussion. It depends on if they're going to create a formula sheet, or if they're just going to use that book as the formula sheet. So that's Torbjørn's area. He's responsible for the written exam in this. Me. I could just mention for the subsea parts that I'm going to discuss it a bit with Runal this week, or next week probably. I don't have time this week. But the possibility of maybe you actually bringing along some of your notes and stuff to the exam there, that you're allowed to actually bring stuff that you've written yourself during the semester. So we'll look into that. I think it's important that you get to know it as quickly as possible during the next week, so that you can actually create the stuff. Yeah. I'm going to talk to Runal about it because I know that he likes the idea of doing it. So if I get the go ahead from him, because after all he's responsible for the entire course. So as long as I get the go ahead from him, then we are going to do that. But that will be clarified next week, just so that you know. And I will try to do it already on Tuesday, so that you get that as quickly as possible. Because if you're going to be able to bring something that you've written yourself to the exam, then you have to know that as quickly as possible, so that you can start creating it during the entire semester. So that's how you will learn the stuff that you're creating. I've had that in a couple of my courses, which I've done myself, and that's been really helpful. I've actually not used it in the exam, but just the fact that I've worked and created this folder with my own notes in it during the entire semester made me so it made me so confident in what I knew that when I got to the exam, I brought it, I put it on my desk, and I never opened it. I just answered everything. I never needed to open the stuff I created in. But the fact was that I knowing that this was something I could bring to the exam to help me with the exam, it made me work even harder with the subjects, so that I actually learned it even better. So I think it's a very good idea to do it like this.
Yes.
Of course, there is one drawback with it, and it means that usually the tasks or the problems in the exam usually becomes just a little bit harder to answer because you have so much to help you when you're doing it. But of course, it also resembles an actual workplace situation a lot more, because if there is something that you're wondering about when you're at work, you Google it. You don't sit around trying to, what was that again? You don't try to remember everything. You just you pop up Google as quick as possible and you just Google it. Or if you know that you have it in a book right beside you, you'll look in the book. But that's I think it's allowing you access to internet during an exam. That's not possible, but but at least allowing you access to a lot more material during the exam. That's fully possible. Yeah, but that was a digression. Has nothing to do with this. I would also recommend the Getting Started Inventor link, which is actually linking the people that have created the software Inventor. They have their own tutorials and stuff, so that's also a very good place to use those two links there, Getting Started and Learn and Explore. You will also see when you are using the program, all over the place there are small buttons with a question mark in them, which are help buttons, which you can press. That will pop up and will show you stuff. Sometimes it links you directly to these pages to show you stuff. Also, if you just hover your mouse pointer, you just hover it above a function that you're going to use, just release your mouse so that it doesn't move or anything. Then after a little while, a tooltip appears, which will show you what this function actually does. So that even with small animations and stuff, it's just showing you what happens when you use this function. So it's a lot of stuff in Inventor. It's possible to learn completely on your own if you just have the time to sit down and play around with the software. So we've used up the CAD laboratory. I've already talked a bit about this. Room 1093, we have it from next Thursday off, 10:15 to 14, and next Friday from 8:15 to 12. Then the room is ours. No one else is allowed to come in and use the computers there, unless if all of you have left during the CAD study or done with what you were supposed to do this week, you've left and there's half an hour left, then there are computers that other people can use, then of course they're allowed to come in, but if you then return, they have to leave, because you are prioritized during those hours. Apart from that, the room isn't always occupied, so you can search it up on Time Edit and just see if there is a lecture in there, and as long as there's not a lecture in there, if it's freed up on Time Edit, you are allowed to go in there and sit there and work. So it's only when there is a lecture on Time Edit that the room is reserved for something. The same goes, we have the Thursdays and Fridays, 2 groups. 4 students. To begin with, we were supposed to have 2, so that's what it says in your compendium here. But of course it's 4, because I talked a bit with Fredrik about it, and we figured out that it's just nice to have all the help we can get, and especially when we are using computers and stuff, because if you fall a bit behind, either I have to stop the lecture and go and help the person who's fallen behind, and then everyone has to wait until I can restart the lecture, or the person who fell behind just has to keep falling further and further behind because he can't catch up. So that's why it's nice to have student assistants with us, and because then they can walk around while I'm doing the lecture. So I can just do brief pauses if I see that there are a lot of people asking questions of the student assistants. I can just pause a bit until they've gotten control over the situation again, and they can help you catch up to the lecture again, so that it's a bit easier that way. So it was very nice that we could get all four. But as I said, for the first 2 weeks, Gabriella is away. I think she was actually going on a cruise. Lucky her. Yeah, seem to have removed that one. But also, the same goes for 2084, the room on the other side of the wall here. If it's not occupied on time edit, then you are also allowed to go in there and work on Inventor if you need extra time, like for the group project and team project. If you need some extra time working on Inventor there to do some extra designs. That was actually one thing I wanted to mention also. The submission deadline for the project is, I think it is something like 23:59 on the 22nd of November. That is the last day of lectures before the exam period. So you have until midnight before the exam period begins to submit the team project. And it is very, very seldomly, at least for the Norwegian students, usually almost everyone passes. You have to have really failed during the semester, basically done nothing in order to manage to not pass at all. But if any of your teams should be unlucky and end up with a fail in the project, you will have a new submission deadline, which will be 1 week after the last exam, so that you get a full week after the last exam to continue where you left off on the project report or on the entire project. That doesn't matter. So then you can just continue from where you submitted at this hour. You can continue work for a full week, and then you can submit it anew. So that will be the second attempt, and then of course, hopefully there won't be a third attempt for anyone. But then we will have to push it to, I don't know, New Year's or a week into 2017 or something. I'm not quite sure how we're going to do a third attempt. I feel pretty confident. Usually, you get a lot of guidance during the semester from me and Torbjørn, so that you do get at least an E or a D. It shouldn't be a problem to get in the project, because if you haven't done anything, then you get a fail. It's pretty difficult to end up with that. The assessment methods. I imagine Torbjørn already has told you about a 4-hour exam. That counts for 60% of the grade. And I've already told you about the folder submission, which is both the project and the 3 individual submissions, which is 40% of the total grade. So the 3 submissions count for 20% of the total grade, so 50% of those 40, so it becomes 20 of the total. And the group project, it also says in here there was 2 to 3 members, but we had basically just miscalculated a bit, because I had said I'm supposed to have 10 groups, and then I somehow figured out that we were going to manage that with 2 to 3 members on each group, which were more than 30 students, so that I don't know where I was that day. But that also counts for 20% of the total. Yep. And as I mentioned, 2016, 2017 doesn't really matter. Yeah, and we have those 2 rooms for use. One problem with Inventor is that it is only available for Windows. So if you have a Mac computer at home and you wanted to work at home with this, then it won't work because there is no Mac version of it. Yeah.
But in that case, is there another alternative?
There are other alternatives. There are other softwares that can do the same, but since we are, you will end up in having a lot of problems because you would have to do it in another software on a Mac, and then you would have to export it into Inventor file format, and then you would have to import it into Inventor, and then you could risk stuff being not quite the same. So that when you're using functions in another program, it might be that Inventor is not interpreting that the same way as the other software is doing. So that is always a little problem with switching between them. So if you have a Mac at home, your only option is basically to use the Windows computers here at school. It's a bit sad. I know, I think it was up until 2010, Inventor 2010. Up until that, there was a Mac version. But after that, they discontinued the Mac version, and then you're just screwed. I have a Mac myself at home, so I don't use Inventor at all. So now we'll begin the technical drawing part. So this is the actual theory that we'll be going through. You will see, just a quick note before we start that one. Right before the technical drawing part in your compendiums, you have subchapter 1.4, Inventor Professional 2016 at home. It's just a brief walkthrough. If you have a Windows computer at home and you want to work with Inventor at home, it's a brief walkthrough of how you register your student email, the one with @hsh.no at the end, the student number at hsh. How you register that with Autodesk, and then you can get to download a free student copy of the program. Actually, you get access to a whole lot of programs. That Autodesk is a really large software company. They have great many programs that they have, and most of them are free for students. So just as long as you have registered your student email, you will have them free for the next 3 years. So that's quite nice. So they also deliver a lot of 3D animation software to the movie industry and stuff. So I know that there's a lot of not exactly Pixar, but similar studios that use Autodesk software for their movies. So that's really cool. Then we'll go on to technical drawing. In the past, and actually to some extent still, technical drawing was done by hand. So in the past, around 2000, when I was doing my vocational studies as a mechanic, we had technical drawing, and then we had this kind of desk where you can sort of tilt it, and you have these rulers that are stuck to the desk, which you slide them about. It's supposed to be completely fixed so that it is exactly 90 degrees and everything. So then you actually did everything by hand. So you used the push pencils with different kinds of thicknesses on your lead. So that's why you have 0.5 and 0.7 and all of this. It's mostly because when they were doing technical drawings, they needed different line thicknesses, and then they needed different thicknesses on their leads. So it's it's been a driving force for that part of the writing industry. I don't think that we would have had different types of lead if it was only used for writing, basically. We still do a lot of technical drawing by hand, but then it is mostly sketching. Like when we have a brainstorm meeting, we would start sketching stuff on a whiteboard or just on a A3 sheet of paper on the desk or something, just to get all of the ideas down into something visual so that you can sort of discuss it more easily. And then afterwards you start transferring it to softwares like Inventor. So that's often what we did in Emenco when I worked there. We used to have a design meeting where all of the engineers, so we were usually 3 or 4 engineers in a project, we would meet up in one of the meeting rooms where there was a whiteboard, and we would just start drawing on the whiteboard all of our thoughts about how we could solve this problem. And then when we were done, we thought that well, we think we have a design that we can continue to work on now. Then we would just pull out our mobile phones and we would just take snapshots of the whiteboard, and then we would go to our separate offices and we would start designing the different parts that we had sketched up on the whiteboard. So it's a pretty good way of working. I also feel myself that you are often more creative if you are allowed to walk around and gesticulate with your hands and do a lot of stuff. You have movement in your body when you're doing this kind of thought processes instead of just sitting at a desk, because you get sort of stationary when you sit there and you don't really get your creative juices flowing. So it's often nice to have the brainstorming session up on your feet and walking about. There was a question about different softwares that can be used, and we have a lot of those. We have AutoCAD, which is also a software from Autodesk, but AutoCAD is mainly two-dimensional. So the Norwegian students, they first learn AutoCAD and then they learn Inventor. But we decided to, when we were going to have this course for you, we decided to rather go full in on Inventor, because you are going to be construction engineers. All of you are going to do the construction engineer. The Norwegian students can choose between construction and process. And in the processing world of a mechanical engineer, AutoCAD is used a lot. So then they have to have knowledge of both. But as construction mechanical engineers, you are much more likely to be working in Inventor or a similar three-dimensional program, three-dimensional software. So then it's more useful for you to get more extensive knowledge of it instead of just a brief fling with it, as the Norwegian students do. We of course have Inventor. There is one called MicroStation that can be used. It is often used for designing very large structures and projects. Creo Parametric is also used for design of mechanical equipment, fairly similar to Inventor. PDMS, it's used for large industrial plants, like Kårstø plant for Statoil and stuff like that. They use PDMS often. SolidWorks is more or less identical to Inventor. You can do mostly the same stuff. They only have a bit different philosophies on exactly how the software does things, so that their functions are a bit different from Inventor, but you will, if you know Inventor, you will find your way in SolidWorks if you switch. SketchUp is actually owned by Google, but it's more used for architecture. But you can also design mechanical stuff in it. And I think there is, at least earlier, there was a free version of it that you could download and use on your own computer. And I think that one was also for a Mac. You could use it on a Mac too. Onshape is a very cool new software, because it is fully cloud-based. So you can, whether you are on a Linux computer or a Windows computer or a Mac, or even on an Android or iOS device, you can use Onshape, because everything is located on servers in the cloud. So that all you do is, if you're on a computer, you open up your browser and you work through your browser to do everything you need to do, just as in Inventor. And if you're on your mobile device, you just open up the Onshape app, and you can do exactly the same as you can do through your browser. So that's a really cool new one. I think they're just 1 or 1.5 years old. So they are really groundbreaking stuff. And I think we're only talking about a year or two before these other guys figure out that, whoa, we need to move into the cloud also, because this is a lot better. So an Onshape is actually free. You can pay for it. You can have a free account through your, if you have a Gmail or Hotmail email, you can create a free account, and then you will only have a limitation as to storage. So So you will just get, I think it's 100 megabytes of storage that is private, no one else can see, and then you can, I think it's 5 gigabytes of storage, so long as everyone else are allowed to see it. So if you're not doing anything that's secret, if you're just doing a school project and stuff, you can make it public so that everyone can see it, and then you can have up to 5 gigabytes in there. Or you can register with your student email, and then you get the full capabilities, because then you have an academic license on it. Yeah?
So the inventor is used for just 3D drawings?
Yeah, 3D models, and then creating 2-dimensional drawings from the 3D models. But you can also use it for more than that. You can do simulations and analysis on stuff. We won't really get into that in this course because we don't have the time for it. We will focus on the 3D modeling and the 2D drawings, which is what it is mostly used for. But you will get, I think it will be, come spring, you will get some other softwares that use what is called FEM, which is finite element method. Finite element method, and the finite element method basically means that it does the same as you do when you're doing handwritten calculations of stuff. But when you are doing a hand calculation, if you have a beam and you're doing a hand calculation on it, you are checking only one cross section of the beam. So you're saying, well, I'm going to look through here, and then you're checking that cross section. What the finite element method does is it divides the entire beam into millions of tiny cubes or pyramids or whatever shapes they use. It depends a bit on what kind of analysis you're going to run. So it just divides it into tiny, tiny, tiny elements, and then it runs the same calculations on all of the surfaces of each element. So it runs the exact same stuff mostly, but doing in a huge scale compared to what you do with hand analysis. And that is actually something you can do in Inventor as you progress, but you have to be more familiar with the program first. Well, as I said, Onshape, you can get the entire capabilities for complete storage. Unlimited storage was the word I was looking for. If you just register with your student email, and you can actually register several emails. So what I did before I started working here, I had already created one with my Gmail account in Onshape. But then as I started working here, and I think it was April or May where they opened up this stuff for the academic account, then I just logged on with my Gmail, and I went to my profile and I added my work email here with the hsh.no. When I added that one, I was automatically upgraded to the academic version where I have unlimited storage capabilities. So then now I can do whatever I want there, and I can choose myself if I want to keep it private or if it is public so that everyone can see it. And the public part is becoming really popular because a lot of people are now investing in 3D printers to keep at home, cheap 3D printers and stuff. And I think it's fantastic that they can actually see other people's 3D models, and then they can download them and print them and test out stuff and just have fun with it. Yeah.
So with the knowledge of Inventor, would you be able to use Onshape?
Yeah. As it is now, Onshape, there are a few of the functions in Inventor that I'm used to using that I miss in Onshape, that they're not there yet. But just on the 8 or 9 months that I've been using Onshape, and I've not been using it on a regular basis, just every now and then I go in and do something. Almost once or twice a month they have an update, because everything is up in the cloud. They don't need to wait until they create the 2017 version to update stuff. So they just update things as they go along. So already a lot a lot of stuff that I was missing or felt were missing in the start, they have been updated. And so they're sort of continually improving the program. So I really like that software. You also have another free possibility, which is FreeCAD. That's an open source. I'm not sure how familiar you are with open source stuff. That basically means that there's a lot of programmers out in the world who also like to do 3D modeling and 2D drawings and stuff. And they've started a project together where they are programming an entire Inventor-like program. So they are together creating this one. And it's completely free. Everyone can join in and program if they know how to program and stuff. So that one also has continual improvements because people are continually creating new stuff for it. So it's also pretty cool. Only for this one you have to keep an eye on it and update it yourself as it goes along. So from old we were doing technical drawings on paper. So sheet sizes are still a thing that we have to take into account. Here is an overview of the sheet sizes. You know the A4, that's the regular sheet size. A5 is half an A4. A3 is twice the size of an A4. And then you got A2, and then you got A1. And there is also A0, which is basically the entire sheet there. So that's really big. I've never drawn on an A0 myself, but I've seen A0s on drawing desks. It just covers the entire desk. It comes in a roll, so you have to roll it. So it's pretty huge. As you can see here, it's 1.2 meters and 0.84 meters. So it's pretty huge when you start with it. Usually, with technical drawings, we stick to A4 or A3. It can be nice when we're doing stuff on the screen. It's never a problem because we can just zoom in or zoom out if we have problems seeing details or anything. But when you're printing it, it's often nice to be able to print it in A3 because you get a bit bigger, so it's a bit easier to see all of the fine details. So usually most printers can't do A2 or A1, so then you have to special equipment. So A3 is usually more than enough to get a good picture of the technical drawing. So that's why we still refer to sheet sizes when we are drawing. So even though we are completely working inside the Inventor and doing stuff there, we still have to choose what kind of sizes we are going to have on our sheets. What happens is when you have chosen a sheet size, you won't really see the difference in the program. The program will still fill your screen with it, so it's not a really huge problem there. But what it will do is it will create an outline. So you can see the gray border around there. That's the background outside the sheet, and then it will create this technical drawing board, and that's more from really advanced technical drawings, because then you can go in and you can say that, well, I'm wondering about something in sector A6, and then you will go in here and you say, well, there is A and there is 6. That means that in this rectangle here, there is something we have to check out. So that's why they have this border where you can sort of more or less like a map, so you can find different regions in the drawing. Usually for mechanical engineers, you are not working on that huge, complex stuff, so it's not really that important for us. But when you do process engineering with huge plants, when you maybe have several hundred meters of piping in all directions going in here, very small scale, then it's can be very useful to have some way of referring to specific locations. You also have a title border down here. And that varies hugely from company to company. Like Emenco had their own design on the title border there. They even had some stuff up here, and that's more or less up to the company you're working for. This one is an ISO standard, so it's a standard from the International Standard of Organization, Standardization Organization. Next. So they have said that this is a nice way of putting it up. So you have the designed by, checked by, approved by. So those are the three engineers that are involved in the process. Because usually in a company you will have one engineer designing, and then he will pass it on to another engineer, which will check it, go through checklists and everything, and see that everything is there. And if he finds some flaws, he will send it back to the designer. Once those two engineers are agreed that, well, now it's as good as it's going to be, this drawing, I think we have it complete, then they send it on to a third engineer who will check it. So, and usually the third engineer is only supposed to check it and not have to send it back for fixing stuff. So something has failed between the designer and the checker if the approver has to return the drawing for fixing. So you have these points. Usually there is a company logo or something in there. You have the titles of the drawing, the drawing number and stuff and you have revisions and sheet numbers in it. We'll continue in room 2008. So we have to change rooms now.